Greetings, my name is Bill Skamrock, and in this Advanced Research WRF tutorial lecture, I will be discussing how the WRF model integrates the equations of motion. I'll also be discussing how the parameters governing the integration need to be set when configuring WRF. There's a lot of material in this lecture. It's only going to provide an overview in most of these areas. For a complete presentation and discussion of these topics, you should look to the WRF-ARW technical note that is available on the web as shown at the bottom of this first slide. We update this regularly with new releases, and that should be considered the definitive reference to WRF for you to look at. There's a lot of topics here. The first half of this lecture is going to be looking at how the model actually works and the numerical methods that are implemented. The second half of the lecture covers how you actually configure WRF for your specific applications that you may have. The Advanced Research WRF Dynamical Core integrates the Navier-Stokes equations forward in time from a given state to produce a forecast. The equations are nonlinear and they cannot be solved analytically, hence we discretize them on a grid to perform that integration. The accuracy of the solutions depends upon the numerical methods we use, which I'll describe, and how fine or not that mesh is. How accurately is our discrete solution, which is an approximation to the exact solution. The equations are discretized on a mesh, and the first aspect of the mesh we're going to look at is the vertical coordinate. For the vertical coordinate, the Advanced Research WRF uses a hybrid terrain-following mass coordinate, and this coordinate is denoted by the variable eta, which is the third equation on this slide here. In the simplest form, terrain-following mass coordinate, eta is defined as the dry hydrostatic pressure at a given level minus the model top pressure divided by the column mass. So if you look at that formula, again, the third equation on this slide, you'll see that eta has a value of 1 at the surface and 0 at the model top, and it monotonically decreases as you go up in the atmosphere. We use the dry hydrostatic pressure, and it shouldn't be mistaken with the full pressure that we calculate in that model, with the full non-hydrostatic pressure. So that dry hydrostatic pressure we use is just part of the definition of the coordinate. It is not a constraint on the solution. So this slide depicts the simplest form of that vertical coordinate we have, which is a terrain-following mass coordinate, because as you can see, the eta surfaces follow the terrain down low, and they relax to a constant pressure at the very top, that constant pressure being pi t, our pressure variable. And importantly, our vertical coordinate uses the dry atmosphere. So the equation to define the mass of the dry air doesn't have any sources or sinks in it. So that's why we use the dry pressure. The second option available in ARW, Advanced Research WRF, which is the default for the real data cases, is to use a hybrid terrain-following mass coordinate. And that hybrid coordinate is essentially defined in the second equation on this slide, which defines the pressure pi for the dry atmosphere d used in the coordinate, what its value is at a given level. And it's more general than the equation you saw on the previous slide for the traditional terrain-following coordinate. It uses this function b of eta, where b of eta is equal to eta when the coordinate is terrain-following, and then it decreases to 0 when the coordinate becomes isobaric, meaning constant pressure. So this hybrid coordinate goes from terrain-following traditional form to, and blends, it's blended, and then it transitions to a full isobaric pressure coordinate, vertical coordinate, at the critical level eta sub c. Again, this is the default in the release of the ARW, and in default also the typical level where it becomes just an isobaric vertical coordinate, is at 0.2. So if you think the typical atmosphere is around 1,000 hectopascals in terms of the surface pressure, then this transition level happens around 200 hectopascal, which is kind of at nominally oftentimes in the vicinity of the tropoplasma. The variables that we solve for in the Advanced Research WRF are listed on this slide here. And essentially, the first one we have an equation for, a prognostic equation for. Prognostic means we solve for the time evolution of that variable. We have an equation for the time evolution. The first thing is the column mass mu sub d, and this is the column mass of dry air. And what I've given you here is that column mass that's also a part of the formula of the vertical coordinate, the top equation there. And we couple that dry air mass with the other variables that we use, or to produce the other variables we use. In this case, the momentum, mu sub d times u, and mu sub d times v, the horizontal momentum components, the vertical momentum components, w times mu sub d, and we use the capital letters for the coupled variables, and also the capital theta, the potential temperature, coupled to the column mass mu sub d. That's the 5 variables that are prognostic. To close the system, we need one more, and we choose a variable that we don't write in conservative form, being the geopotential, g times z. The mass coordinates can move in geometric space and height. They go up and down based upon the change of mass in the column, and we have an equation to predict what the new height at a given point will be, and that's the equation we use to close the system. So these are our prognostic variables. Variables that are not prognostic we compute, and these are called diagnostic relations, and we use that to compute other variables. For example, the definition of the vertical coordinate as the dry hydrostatic pressure is the first equation you'll see on the slide up top on the left, and we use that given that we have prognostic equations for the column mass mu and the geopotential eta. We can diagnose this variable alpha sub d, which is the inverse of the density, 1 over the density. And additionally, we have an equation of state for the atmosphere, which we could diagnose the pressure. And we also have our prognostic equation for theta is actually cast in terms of this theta m. Again, the subscript d, when you see it in the equations, denotes a dry atmosphere quantity. So the full density, for example, is the dry air density multiplied by 1 plus the mixing ratios of the other components of the atmosphere. Listed here are vapor, cloud water, rainwater. That may also include other things for when you have more complex microphysics, etc. The last thing I want to touch upon here is that while we prognose, so we have a prognostic equation for the vertical velocity w, we also carry a second nominally vertical velocity denoted omega. And omega is essentially the velocity that's normal to a horizontal coordinate surface, and they're depicted by the variables and arrows in red on the plot of a vertical cross-section of the WRF-ARW mesh here. And we use those to calculate fluxes through that surface. And we have an equation which relates omega to the other velocity components u, v, and w. So what do the full equations look like? That's what you're going to see in this next slide. We start out with the time rate of change of our prognostic variables. As I noted, u, v, w, the components of momentum, the column mass mu sub d, the coupled potential temperature mu sub d times theta. We also have an equation for what we call scalars or tracers, which we denote with the variable q, and that q could be moisture, it could be number concentrations for multi-moment microphysics schemes, it could be chemical species, aerosols, anything else you want to look at. It could be just a passive tracer that you put in there just to see where things go. And finally, we have our equation for the geopotential. This is time rate of change. We're going to integrate these forward in time. The first term you see typically is transport terms, or what are called advection terms also. We cast them as a flux divergence in these equations. So everything is inside the derivatives in x, y, and eta, our coordinates. We state that these are now in flux form, and these give us a form that allows us to build in certain conservation properties, which I'll talk about shortly. The geopotential is left in advective form, the final equation on the slide that you see here. And what makes it advective, essentially, is you'll notice that velocities are not contained inside the spatial derivatives. So that means it's in advective form. The reason we do this for this equation is putting it in flux form, which we could do, is just not, doesn't gain us anything in terms of conservation properties. The next set of terms in our governing equations and our prognostic equations are the pressure gradient terms for the momentum. See the horizontal pressure gradient terms and the vertical pressure gradient term. These pressure gradient terms, we're on a terrain following pressure coordinate, but our velocities are the horizontal velocities that are constant height. So there's two pieces to these pressure gradient terms. The gradient along the horizontal coordinate surface plus a correction to bring it to constant x or y, depending upon you, whether you're looking at u or v. And then finally, the vertical momentum equation. This pressure gradient term, for a hydrostatic model, we would throw out the vertical momentum equation and just use that pressure gradient, that hydrostatic pressure, to define the atmosphere. But here, it's just part of the vertical momentum equation that you see. And what's left after that are other terms in the equations, which you'll have many lectures about in this Advanced Research Wharf tutorial. They include some aspects of numerical filters, some of which I'll talk about in this talk later. They're also where the physics forcings occur, and you'll have many lectures about the physics, and a lot of what you do and how you configure your model will be related to which physics you choose to use and how you configure them when you use them. Also, the projection terms that allow you to map this onto the Earth and the sphere, or pieces of the Earth. And finally, as I mentioned, that geopotential equation also has a term in it that essentially renders it in non-conservative. So it's the reason we don't cast that one in conservative form, because of that GW term that appears at the end. At the equations, we have the diagnostic relations that I mentioned. So we have our prognostic variables that we advance forward in time, and any other quantity we want to compute, we use the diagnostic relations to compute them: pressure, density, and other aspects for which we need them. First, we're going to look at how we integrate the equations of motion in time. So if you remember from the last several slides, we have a time rate of change of the prognostic variables equals a lot of stuff. Much of it are spatial discretizations on the mesh, or things that come from physics or somewhere else. We can just look at the time integration as a way to take all the other stuff outside of the time rate of change of the prognostic variables and just treat it as something that's a given that may vary in time and integrate it. So within Advanced Research Wharf, we use a certain variant of Runge-Kutta time integration. There are literally an infinite number of Runge-Kutta schemes, and we use a third order variant that uses 3 steps to accomplish advancing the solution forward in time, one time interval delta t. And it's depicted here on the slide. The first step is we take the solution at time t, we evaluate all those other terms that aren't the time derivatives, and they're denoted by the right-hand side RHS terms. We multiply that by delta t over 3, add it to the solution that we started with at time t, and that gives us a predictor nominally at a third of a time step forward. Then we take that predictor, denoted phi star here, and we again evaluate all those right-hand side terms, or most of them as you'll see, not all of them actually, to get a new estimate of what those right-hand side terms should be. And then we take the step again starting at time t with that new estimate, and we get another predictor, here phi star star. And then we repeat that process once again, reevaluating the right-hand side term, add it again to the solution at time t, multiplied now by delta t, and that gives us a new solution at time t plus delta t. If we look at a simple analysis of what this scheme does, for example, taking the oscillation equation, where it's written as the time derivative of phi is equal to ik phi, where k is a wave number, I is the imaginary square root of -1. And you look at the discretization, the time discretization on this slide, what you'll see is that the amplitude of the solution after the time step will be 1 minus k delta t over 24, that quantity to the fourth here. And what that means is two things. One is that we know the exact solution should be 1, that the amplitude should be unchanging, it should just be propagating. However, we see that the amplitude is slightly less than 1. Now, delta t is small, k delta t will be small, so there'll be a slight decay in that, which is a good thing because the solution won't amplify. And the second thing is that it's delta t to the fourth. Now, k delta t is a small number, and hence the error is small because we're taking a small number to the fourth power. So given that that's to the fourth power, it means that this scheme is third order accurate in time for the linear terms. The non-hydrostatic equations solved in WRF include acoustic waves, or sound waves. These waves propagate very quickly, order 300 to 350 meters per second. This would limit the explicit Runge-Kutta scheme to very small time steps, and it would be very expensive if we tried to integrate everything within that Runge-Kutta time integration. There's only a small number of terms in the equations that we're solving that are responsible for the acoustic waves. So what we do is we integrate with a time splitting scheme that essentially uses a different integration method for the acoustic waves, here noted as the fast waves in the equation at the top of this slide, as opposed to the other right-hand side terms that we've denoted here with this operator L of the slow modes, essentially everything else other than those acoustic terms. Although for the fast modes, we also put the gravity wave terms in there because it turns out to be very easy to do. This different integration method for the acoustic modes is combined with the Runge-Kutta time integration. It's contained within it. And the equations depicted here in the red box, the equations depicted pictorially, show the 3 time steps in the Runge-Kutta scheme. And it also shows inside those time steps are sub-steps where we integrate the fast mode terms, the acoustic mode terms, and evaluate them at every sub-step here within a different integration scheme that's coupled with the Runge-Kutta scheme. For the first Runge-Kutta sub-step, that step to delta t over 3, we just do 1 acoustic time step, no matter what whether it's stable for that 1 step or not. It turns out it doesn't matter. For the subsequent steps, though, the second and third Runge-Kutta steps, we take some number of acoustic steps in each of those time steps. For example, depicted here, we're taking 2 acoustic steps to get to delta t over 2, in that second Runge-Kutta step, and we're taking 4 to get the full time step evaluated and the new solution, to produce the new solution. We could, for example, take 3 for that second step, and then take 6 for the final step, the final Runge-Kutta step. And we set that acoustic time step size based upon what's needed to maintain the stability of that acoustic time step, of those acoustic modes. Here are the acoustic step equations that we solve on the substeps of the Runge-Kutta scheme. The top equations for the horizontal momentum, U and V, and that's the first part of the solution we step forward over the acoustic steps. This approach is called the forward-backward scheme, and that's the forward step. Next, we step forward the equation for the column mass, mu d, in the atmosphere. And you can see, if you look at the second equation, it uses the solution for the horizontal momentum at the new time level. It also uses that vertical velocity omega at the new time level that is actually diagnosed using this second equation. So the way we advance mu d is we integrate throughout the column. That gives us the updated mu, and then we back out what omega is. So this is how we diagnose omega. This approach is used in hydrostatic models in addition to non-hydrostatic models. So this approach for integrating that equation is almost ubiquitous in mass coordinate formulations for both hydrostatic and non-hydrostatic solvents. That's what we do in WRF. That is the forward step. Given the new updated velocities and U and omega, we can now advance the potential temperature theta, and that's using those new values, and that's called the backward part of the step. So we've advanced the horizontal momentum, the column mass, and the potential temperature. We treat the vertical velocity and the geopotential differently. And the reason that we have a different approach here is that the vertically propagating acoustic modes also travel very quickly, at 300 to 350 meters per second. The vertical grid is much finer typically than the horizontal grid. For example, you may be using a horizontal grid of a few kilometers or tens of kilometers or 100 kilometers. That vertical grid in the boundary layer is going to be tens of meters, maybe 100 meters. So the time step restriction from an explicit scheme is going to be very problematic. It's going to make the scheme, if we want to integrate explicitly, very expensive. So what we do is we integrate the vertically propagating acoustic modes implicitly. And that implicit integration shows up in the W equation, where we have this overbar tau. And that means we're taking some value of that term at the old time level and the new time level. And likewise, in the geopotential equation, you'll also see the GW term has an overbar tau to it. Again, the old time level and the new time level. That means that now the solution at the new time depends upon, has a dependency on it that makes it implicit. We have to know that solution to compute it. And it results in a very simple tri-diagonal system in the column that can be solved. And that removes the time step restriction on the acoustic integrations from the wave speed of the acoustic modes. So that's why we do this. So this is a forward-backward scheme with vertically implicit integration of the acoustic modes. This approach here has been around for a long, long time, or quite a long time, since the mid-70s. And it's used in lots of models, not only just WRF, but COAMs, ARPs, the Cosmo model. A number of models around the world use this approach here. Most of the models that are doing certainly explicit time integration are using these approaches in the non-hydrostatic systems. To summarize the time integration scheme, we have it written here as pseudocode, and it works as follows. There are two main loops. The Runge-Kutta loop cycles over the three Runge-Kutta substeps, and within it are the acoustic steps that divide these Runge-Kutta steps in smaller chunks be stable for the acoustic or sound waves. In the Runge-Kutta step, the first thing that happens is that one computes advection, pressure gradient, buoyancy terms, etc., a lot of the right-hand side terms. The next thing that happens on the first Runge-Kutta step, it computes all the physics forcing tendencies. It only computes them once and saves them for use in the second and third steps. The physics are expensive, and forward in time integration, that one computation is sufficient for accuracy of the solver. Then mixing terms and other non-RK dynamics terms are computed and saved. Then they're assembled, and then we start the acoustic steps. The acoustic step uses the forward-backward scheme that we depicted on the previous slides, advancing first the horizontal momentum, then the column mass, then potential temperature, and then finally, in the semi-implicit approach, the vertical velocity and the geopotential. We also save off the time-averaged momentum fluxes for use to advect the scalars after the acoustic step is complete. And after the end of the Runge-Kutta loop, we have one more physics call to microphysics because we want at the very end of that time step that to be the last update to the solution so that it has the saturation adjustment that comes from the microphysics. And that's what you see in your output. And that's the end of an acoustic step integration. Having reviewed how WRF is discretized in time, let's now examine the spatial discretization. The prognostic variables in WRF are placed on what is called a C-grid staggering within the integration scheme. On the left is a horizontal cross-section of a WRF grid cell. In the center of that cell are the scalar prognostic variables. In this case, the column mass, the potential temperature, and the mixing ratios of whatever other species are contained. And they are nominally the cell averaged variables. On the cell edges are the momentum, and specifically the momentum that is predicted on a specific edge is the momentum that's normal to that edge. So in the horizontal cross-section, we have, in the x direction, we have the u momentum, nominally from west to east or left to right. And we also have the v momentum, the north-south to north velocities, placed on those edges. And these momentum and velocities are normal to the edge. On the right-hand side of this figure is a vertical cross-section of the C-grid discretized ARW numerics. And the variables there, again, in the cell centers are the scalars. And in the horizontal direction, in this case x, we can see the u velocities. And in the vertical direction, we have the vertical velocities, omega, which is the normal velocity, w, which is the one that's radially outward from the Earth. And then finally, we also define the geopotential at the w and omega points, because you look at the geopotential equation, its main term in there is g times w, so that's why we place it there. Next, we're going to look at advection or transport and how we build in the conservation properties into the WRF-ARW solver. The solver itself will conserve dry air mass and scalars exactly, meaning that you don't lose any mass of scalars due to advection except what flows into or out of the domain based upon whatever you specified in your lateral boundary conditions. So the first step in understanding how transport works, let's look at the equation for the column mass mu d that we use as a prognostic variable in WRF. Here is another depiction of the control volume, a vertical cross-section, and we're just going to look at one horizontal dimension and the vertical dimension. It's sufficient to understand how mass is conserved, in this case dry air mass. The mass in that control volume is going to be equal to the area of the control volume, delta x times delta eta, times the value of the dry air mass in that volume, mu, because delta eta will be the fraction in that volume in the vertical. So you can see that'll give you the mass in that control volume at time t. And you can also depict that in terms of other variables, in this case the the dry air density in delta Z, if one wants to think of it in that way. So that's the mass at a given time. If we look at our conservation equation for the dry air mass, the discrete form is written as shown right here. There's a time rate of change of the mass in the control volume. So that's mu at the new time level minus mu at the previous time level. And what you can see is that we multiply that by delta x delta eta divided by delta t. That's the change in the mass in that control volume. And that is going to equal fluxes through the boundary. Here we got mu times a velocity u, or mu times a velocity omega. If you remember, those variables, mu u, mu omega, are essentially our prognostic variables. We can relate omega to w and the horizontal velocities through an equation that's very easy to implement. So, and these are called the mass fluxes through the control volume face. If we look at the horizontal fluxes, you can see we've got a difference from a flux into the volume, mu u times delta eta. So that's the amount flowing into that volume, minus, in the green box, mu u times delta eta on that right-hand side edge. That's flowing out for a positive velocity. And we're saying that, okay, the change in mass inside the cell is equal to the difference in what's flowing in and out in x. And likewise, in addition, it's also what's flowing in and out through these vertical faces right here with the velocity omega that's normal to that surface. So those are the other two terms. And a key aspect of this is that the same individual flux on a cell edge that's used to update one cell on that edge is also the same flux that's used to update the other, meaning that mass is not lost. If it's flowing out of one cell, it's flowing into the other cell and is taken into account when that other cell is updated. This way to conserve mass exactly within the solver is termed essentially local conservation. We have enabled local conservation, exact conservation in our solver. And because we have local conservation, it means we have global conservation, meaning that mass is conserved over the entire domain because you can integrate over your entire domain and all the changes in mass will cancel each other out and you'll be left with the exact same mass except for what's flowing into and out of the domain based upon the boundary values that you're using to drive the regional version of WRF. That will specify how the mass is changing in the entire control volume. But internally, that mass is conserved exactly. So, okay, we conserve dry air mass. The question is, how does that enable us to conserve the mass of other scalars and other quantities in our system? So one of our prognostic variables is the potential temperature coupled to the column mass mu. This is essentially a form of entropy. And the other variables, for example, moisture and chemical species and stuff, you have masses of this in the atmosphere, and that's also conserved. And the conservation of those quantities is linked to how we conserve the dry air mass, because the mixing ratios for water vapor and chemical species is just the mass of that species divided by the mass of dry air. So the conservation of scalar mass is based upon the conservation of dry air mass. And that's because the scalar mass is just the dry air mass times the mixing ratio for that scalar quantity. And that mixing ratio is itself the mass of the particular quantity divided by the mass of dry air. So when you multiply mu times that, you get the mass of that particular scalar. If you look at the mass conservation equation, just copied it from the previous slide, and it gives you what the change of mass over the time step is. We looked and saw that it was mass fluxes through the control volume faces. Because the same fluxes are used to update the cells that share that edge across which mass is is fluxing, that we get exact mass conservation internally in our system locally. So the scalar mass conservation equation looks just like the dry air mass conservation, where everywhere you see a mu, you multiply it by the mixing ratio, in this case denoted phi. And that's given here. And that results in exact mass conservation for all of the scalar species that one has, in addition to dry air entropy, for example, because theta is also part of the flux variable that we have. All those properties that we got for the dry air mass carry through to the scalar air mass. Transport terms also need to be evaluated for momentum, where the control volumes are shifted relative to scalars, given that the momentum is defined on the cell edges. In other respects, the evaluation of momentum transport is the same as that for scalars, so we won't go into any more detail there. The quantities we are transforming are defined at cell centers, but as we've seen in previous slides, we have to specify these values on the cell edge to compute the flux of that quantity. How one specifies these quantities lie at the heart of what are called transport or advection schemes. And what we're going to talk about next is what options are available within those schemes and how those options operate, what you can expect from the solutions given specific choices in those options. The main flux options in WRF are denoted by the spatial order of accuracy of the flux divergence operators that they produce. So we specify a flux and then we compute a flux divergence. And how accurate is that flux divergence? In WRF, one can choose among second through sixth order flux operators. The default for the WRF horizontal flux operators is the fifth order scheme that's given in this slide. So what you're seeing here is first, here is the flux divergence across the cell, given in this notation where the flux is denoted as F on the right face minus F on the left face. And how do we compute what that flux of the variable psi is? Well, that's the formula that's given below. We don't want to go into details here because it comes from a paper back in the 90s. And if we look at what the flux divergence, when we plug that formula in for the flux equates to, we get the following. For the fifth order flux, which is the default in WRF for horizontal transport, it is equal to the sixth order flux minus this other term here. And this other term is an approximation for the sixth derivative of psi times a Courant number, U delta T over delta X. You can see that from the formula. That's a dissipation or diffusion term, a hyperviscosity, if you will, hyperdiffusion. And in the second through sixth order schemes, the odd ordered schemes, for example, the fifth order scheme, is equivalent to the next higher order even scheme, in this case the sixth order scheme, plus a dissipation term of that order. That becomes your error there effectively. And that dissipation term has a viscosity or hyperviscosity that's proportional to the Courant number, U delta T over delta X, for the X direction flux divergence. Two options exist within the transport schemes for WRF. A positive definite option, which means that one does not allow the solution to become negative. For example, negative mixing ratios state that there's negative mass in a cell, and that's non-physical. There's also a shape-preserving option, also known as a monotonic option, which limits the solution in a way that does not produce new maxima or minima as part of the transport process. And this is something that the solution should obey based upon the continuous equations. Now, ARW transport, it is conservative, but it's not positive, definite, nor shape preserving. So here's a depiction of a test where we're just looking at transport in one dimension, X, and we've got a mixing ratio that's 0 to the left and some positive value to the right. You take a time step, and all of the schemes that I described, the second through the sixth order scheme, are going to produce with a very sharp feature like this, typically overshoots and undershoots. You'll get both negative values, which are non-physical, and positive values, which are also non-physical, but harder to identify, where the solution is now greater than anything that existed before the step. So you see these overshoots and undershoots. Now, one way of fixing, for example, the undershoots, the negative mixing ratios, which are clearly non-physical, is just to remove these negative values, just chop them off, set them to 0. But in doing so, because the base transport is conservative, removing negatives mean you now added mass to the system. So even with these overshoots and undershoots, we're conservative. So if we integrate across the domain, we're getting the same mass at both the beginning and the end of the time step. So now if you start removing negatives, you're essentially adding mass to the system, to that integral. So that's a bad thing. So what do we do in order to allow for positive definite solutions and shape preserving solutions while also maintaining our conservation? And our solution is as follows. In the last step of the scalar update, we apply what's known as essentially a form of flux-corrected transport, which goes back to the late 70s paper from Zalasek and many others have incorporated versions of this into their models. Essentially, at that last step, we compute all the fluxes that go into the flux differences to do the update. We can decompose those fluxes into a pure upwind flux, which is a first-order scheme, which just says take the mass from the upwind cell, just that, and not that more complex formula I showed you earlier for the higher-order schemes. We can decompose it into a correction in that upwind thing, and that correction being the full flux we just computed minus the upwind. The upwind flux is guaranteed to be positive definite and shape preserving. So it's okay. So we can do a partial update with that upwind flux, which is very low order, very dissipative, it turns out. And then we can say, does the higher order correction cause the solution to be either not positive definite, if that's the option we have, or not monotonic? Does it create new local maximum or minimum? If it does, we can then scale that flux. And in essence, taking less of that flux until it gets us just to the point where the solution is positive, definite, or monotonic with the maximum amount possible of that flux, and then update the full solution with that renormalized flux. And that's what we do, and that's the scheme, the flux-corrected transport scheme of Zalasek. Given that you're rescaling the fluxes and then doing the flux divergence, again, that same flux is updating both cells which share the edge that flux is defined. Hence, you maintain the conservation properties, the exact local conservation of the scheme, hence the global conservation, in addition to getting the positive definite and or the shape-preserving monotonic properties that one wants from your transport schemes. Example shows how that actually works. Here's an example, again, one dimension in X, of a top hat, and the top hats are given in the green dashed lines. That's the solution at time 0, and it is transported through this periodic in X domain, so it's transported from right to left. It goes out the right boundary, comes back in the left boundary, and goes right back to where it was initially. There's a constant wind speed here, so the solution at time 0 and time capital T, the end of going around one step, should be exactly the same, and the green dashed lines depict it. The red lines depict what comes from application of the WRF advection scheme. On the top panel is the 6th order scheme, on the bottom panel is the 5th order scheme. In the leftmost solutions, there's no limiter. It's not positive definite, nor is it shape preserving. And as you can see, the 6th order scheme produces a lot of overshoots and undershoots, but arguably it's actually the most accurate one, depending upon what kind of error norms you use. The fifth order scheme, which has some dissipation in it, if you remember back several slides, it's much smoother. A lot of those overshoots and undershoots are gone, but not the ones right next to the top hat. Those remain, and hence you get negative mixing ratios in addition to overshoots above the original values. Now, if we enable the positive definite limiter that was described on the previous page, you can see that the values below zero are gone. However, the overshoots are still there. And if you'll also notice here, I think it becomes more clear that the sixth order scheme is just slightly more accurate. You can see where the steep gradients in the top hat, it defines the top hat better where it goes up and back down than the fifth order scheme. The fifth order scheme smooths it out a little bit. But the cost is more of the overshoots and undershoots for the top part of that top hat there in the sixth order scheme. And finally, if we look at the monotonic limiter, which is the rightmost panels, you can see that both the overshoots and undershoots are eliminated, and you can see the sixth order scheme looks a little bit more accurate than the fifth order scheme, although there's not a lot of difference in the grand scheme of things. As you might guess, the least expensive scheme is to use no limiters. And let's say that has a cost of a certain cost. If you look at applying the positive definite limiter, that will be about another 50% or maybe 30 or 40% more expensive than not turning it on. So it adds a significant cost to the scheme, but you get a very nice physical property of not getting negative mass in the scheme. This, using the positive definite limiter option, is the default in WRF, and that's based upon experiments we did in NWP settings at convection permitting scales, horizontal mesh spacings of order a few 3 or 4 kilometers, and we found that if we didn't use the positive definite option and you just chopped off the negative mixing ratio values in the moisture, they were showing up as more moisture in the atmosphere and more precipitation, too much precipitation. So we had a significant positive bias in precipitation, and by using the positive definite option, that bias is gone. So that's why it's a default. If we move to the monotonic option, which looks very nice, it is order twice as expensive as the base scheme. So it adds a significant amount more cost. When we look at the NWP configurations for precipitation, we do not see significant difference in the solutions when using the monotonic or shape preserving options versus the positive definite option. So that's why we've just chosen positive definite as a default in WRF. However, when you're doing applications that include chemistry, in those applications for the chemical species, the monotonic option is often used because chemistry can be strongly nonlinear, and those overshoots that come about with the positive definite scheme can cause more problems in chemistry applications. So chemistry, you use the monotonic option, or at least that's the default in the configuration. Also, you may want to use it for if you're using a multi-moment or some of the multi-moment microphysics schemes. In the remaining portion of this lecture, we'll look at how to set the integration parameters. Usually, these are found in the nameless.input file that controls the Advanced Research WRF integration. The transport schemes, here's the list of parameters that you will see, and it sits in the dynamics section of that nameless.input file. There are a variety of parameters that control the horizontal and vertical scheme, the second through sixth order options. There's also ways to control individual classes of scalar transport, be they moist scalars, chemical species, tracers, turbulent kinetic energy that's used in some of the LEF schemes. These are all available to you. The positive definite limiter is enabled by default in WRF configurations, and the default also includes the fifth order and horizontal and third order and the vertical scheme. Mentioned earlier, chemistry applications typically use the monotonic limiter, which is option 3. Option 5, which is a positive definite we know, is used in some applications where you have multi-moment physics. And the reason that that's sometimes used is that it's found that the correlation between mass and the number concentration in these multi-moment schemes is better maintained by the WRF scheme than by the base transport schemes in WRF, the second through sixth order schemes, even when they're running the monotonic option. WRF stands for weighted, essentially non-oscillatory, and you'll find more information about that with references in the tech note. So we're at the point where we've looked at the transport schemes and how to set those up. Let's go back to the time integration. We have our third order Runge-Kutta time step. That's the main time step in WRF. That's a delta T. That is the time step that you're advancing the solution from T to T plus delta T. That shows up right at the top of the nameless.input file in the domain section. And you'll see two ways to specify it. There's one time step that's in integer seconds. And that's just what it is. It's an integer second. Then there's a second time step, which is a fractional time step, where you specify the numerator and the denominator. So you either specify it one way, that first one, or the second way. The reason that there's that second way to specify it is when you want to specify a time step that's a fractional second. For example, with very small meshes of a few tens of meters, you may want to use a third of a second. And here you'd specify 1 and 3. And then the infrastructure in the code will take that fraction and make sure that when you multiply it, when you take 3 time steps, that you end up exactly at 1 second and not an epsilon away from 1 second by adding a third and a third and a third. You won't have 0.99999, for example. That's why that's there. Guidelines for selecting that time step is that the time step in seconds should be about 6 times the horizontal grid length in kilometers. So as noted in this box, if you had a 10-kilometer delta X, you would choose a 60-second time step. This is just a rule of thumb based upon real data applications where the maximum wind speeds, for example, in the jets, are maybe something of order a little more than 100 meters per second, maybe going up to 140, even 150 meters per second. That time step will be stable. After setting the main Runge-Kutta time step, you then move on to setting the acoustic time step. That acoustic time step is set as a fraction of the Runge-Kutta time step. And in the nameless.input, in the dynamic section, you'll see a parameter that's labeled time step sound. Now this is actually not the time step. It is the integer by which you divide the Runge-Kutta time step to compute the acoustic time step. So that integer right now, the default for ARW is 4, meaning it takes 4 substeps, acoustic substeps, over that Runge-Kutta time step. So even though it's named time step sound, it's actually an integer that divides the Runge-Kutta time step to give you the acoustic time step, and it sits in the dynamic section in the nameless.input file. So you've set your Runge-Kutta time step, you've set your acoustic time step. If either of those time steps are too big, it is likely that WRF is going to blow up. It will abort quickly because there'll be a floating overflow. If that happens, there's 2 things you should try to do to try to diagnose what happened when the model blew up quickly. And quickly means a few to less than 10 time steps. First thing you can do is decrease the Runge-Kutta time step, because this will also decrease the acoustic time step. And the second thing you can do is, so if you try the first one, you decrease the Runge-Kutta time step, and you find out it's stable. You can go back and leave the Runge cut time step the same and try the second one, which is just to increase the time step sound integer. Remember, it has to be even, so it divides evenly to the half time step. And if you go back to the time splitting, you'll see how that works. And this will decrease the acoustic time step, but it doesn't change the Runge cut time step. If doing option number 2 gives you a stable integration, then that's a clear sign that it's an acoustic instability that caused the model to blow up. If doing 1 works, but doing 2 alone doesn't work, then that suggests that just maybe the Runge cut time step is too big. And in that case, just decrease it and leave it there. So this is what you want to try to do. If you try both of these options and decreasing the Runge cut time step, try a factor 2, for example, to start. If the model's still unstable, and it goes unstable very quickly, a handful of time steps less than 10, then that really suggests that there may be something wrong with the initial conditions. Something's not set properly, there's denormalized numbers in there, something to do with the physics is problematic, and then you maybe need to look a little harder as to what goes on, or try rebuilding your initial conditions, etc. But if just decreasing the time step gives you a stable integration, then that's a suggestion that the time step was just too big. Why might that be? Because you followed the directions at 6 times the delta x in seconds. The projections that WRF uses to put a rectangular mesh onto the sphere, those projections and the grid spacing are the correct number for the central cell in the grid. As you move towards the edges, the grid cells get somewhat smaller in physical space, and the time step restrictions for the acoustic waves and the advection, etc., are based on the physical sizes, not the computational mesh, but the physical mesh as it's projected to the sphere. So it may be that as you move towards the edges of the meshes, the mesh sizes are getting small enough because of the nature of the projection that you've run into an unstable situation, and that's why you need to decrease your time step somewhat. There are a number of filters in Advanced Research WRF, and the next several slides I'm going to go through what these filters are and whether you need them or not, and what you can potentially play around with if you're seeing behavior that you want to see how the filters are affecting it. One of the first ones is a 3D divergence damping, where the divergence is the 3-dimensional divergence. This damps acoustic modes preferentially, and it's put into the system by putting in divergence damping into the momentum equations, in this case by forward centering the pressure, as given in the red box below. So we do this to damp the acoustic modes. We have a damping coefficient of 0.1 as recommended. The coefficient itself sits inside of the dynamic section of the nameless.input, and the variable is SMDIV, which nominally means small step divergence damping. The model itself will run if you set this to 0. You may see a little bit more noise in the pressure field when you turn this off, but the model will typically run stably because the other filters that are active in the model are sufficient to keep it stable. So you can set this to 0 and it will run fine. There's another damping mechanism for acoustic modes that apply to the vertically propagating modes. In the vertically implicit integration of the acoustic modes that go in the acoustic integration, the time split approach, there were time averages over both the pressure gradient and buoyancy force terms in the vertical momentum equation and over the W term in the geopotential equation. And those time averages, the averaging operator, the overbar tau, is given in the third equation on the slide. And essentially, it's just a weighted sum of the new time level and the old time level. By weighting the new time level more than the old time level, you're forward centering that operator. And that introduces damping into the system for the vertically propagating modes. In the case of ARW, the default is to set that term beta, which forward weights the new time, to 0.1. That parameter is EPSSM. That's in the dynamics part of the nameless.input. When you're running real data cases in ARW and some of the idealized cases too that have terrain, that off-centering is necessary for stability. And there's a paper written about this, a note that you can find in the tech note, referenced in the tech note about this. So you cannot set this to 0 and expect that the integrations will remain stable. This has to be something other than 0, positive value. 0.1 is recommended. If you have very severe topography on the mesh, you're at high resolution over very mountainous terrain, like some in the U.S., certainly down in South America with the Andes, and you find your model's going unstable very quickly, you may want to bump this up to 0.2 or even higher, because that may regain you stability. So this damps the vertically propagating acoustic modes, but it also has a piece that's related to the three-dimensional acoustic modes when terrain is in play. So again, this one is required. You can't set this to 0, at least for real data applications. The upper boundary condition in the Advanced Resource WRF model is constant pressure. And the surface at the top here, waves can propagate based on that, because that upper surface is moving up and down. And the external modes, which essentially, you can think of these as waves in the bathtub. They're the wave number 0 mode in the vertical. These aren't physical. These are just a consequence of our upper boundary condition. And we can damp those modes by damping the vertically integrated divergence. And that's what's essentially the vertically integrated divergence is the horizontal divergence averaged in the column. And that's what we have here, the first equation. And when we put that damping into the momentum equations, we damp those modes. The default parameter here recommended is 0.1. You'll find that in the dynamic subsection of the nameless.input, and the variable is emdiv. This is primarily there for use in real data applications. And what happens is that initial imbalances in the WRF fields and real data applications will generate a bunch of external modes, and these modes will propagate away, and when they hit the boundaries, they're absorbed by the lateral boundary absorbing layer, and they go away. If you want to look at the solution very early times in forecasts and time integrations, those waves will be present. You will see them if you don't damp them with this external mode filter. The model will remain stable without it, so you can set that coefficient gamma sub e to 0, and it'll be fine. But the waves are there. So if you want to look at the early times of the solutions, you should set this, leave this parameter at the recommended default value, and those waves will no longer be there. Again, for real data applications where there are imbalances because you're interpolating from another analysis, it's just to clean up the early time solution. Let's go again. The next filter we'll consider is vertical velocity damping, and its purpose is to damp large vertical velocities that will cause the model to go unstable. These instabilities are usually show up when the model physics aren't doing what they should do. Oftentimes, for example, a convective parameterization is not sufficiently active when there's significant instability in the atmosphere that will cause the explicit motions to try to release that instability, and you end up with instability in the model because the vertical velocities get too large. To activate this filter, you have to turn it on. It's off by default, and there are two parameters when it's on that you have access to. One is what that critical Courant number is. One is a typical default value, because you know if you get to 1.5 or 2, when the vertical velocities increase, that's the region where instabilities may cause the model to whole integration go unstable. So the default critical value is 1, and the damping rate is, this gamma sub W is 0.3. If you activate this filter, the information about when it turns on and how often it turns on and where will be written to the output logs, so you can look after the fact to see if the filter actually activated after you've turned it on. If it hasn't activated, then you're good. If it has, then you should see, is it active in just a few spots here and there, or is it active over a wider region? If it's active over a wider region, that's an indication that you've got more problems than just a parameterization maybe not doing what it should do. If it's active just here and there, then that's probably fine, and you've stabilized your solution and you haven't lost your entire integration just because one column is unhappy. Next filter that's part of the dynamics, but can be, many people consider it part of the physics, but I consider it dynamics, is a second order horizontal mixing based upon the horizontal deformation. And this was first popularized by Smagorinsky back in the 60s, and the formulation is given here. For real data applications, this is on by default, and in the dynamics part of the nameless.input file, the diffopt1 KMOP4 is what activates this. The Smagorinsky coefficient of CS equals 0.25 is the default value and what you should see. Now you may look at this and say, well, why do I want more dissipation? And in these nonlinear integrations in the atmosphere, we have downscale cascades of energy and entropy. So when in that cascade, which takes energy in the large scales and brings it down to smaller and smaller scales, or entropy for that matter, when it gets to the smallest scale that can be represented on the grid, the 2 delta X scale, it can't go anywhere else. In the real atmosphere, it goes down to where the molecular viscosity dissipates it. But we don't have resolution down to that scale, obviously nowhere close. So we have this formulation here to help remove that energy when it gets to the smallest scales in the model, because this is where the deformations will be largest. So this, along with the odd-ordered aspects of the transport schemes, provide the damping in the model to remove energy from the cascade, from the downscale cascade. Another filter we have is active in the uppermost layers of WRF model, and that's a gravity wave absorbing layer. It is based upon implicit Rayleigh damping for the vertical velocity, and this is specifically for running in the non-hydrostatic configuration of WRF. If you look in the ARW technical note, you can actually run the WRF model at a hydrostatic basis. In terms of with hydrostatically, you don't have access to this filter. But the reason that you want to have this on is that gravity waves propagate up vertically. So you have flow, let's say, over topography or from convection. They trigger gravity waves that propagate vertically. As they go up and up and up, when they get to the model top, if they haven't broken, if the waves haven't broken as they propagate up, if they make it to the model top, they are reflected back down into the domain. And this contaminates the solution, because ultimately they should keep propagating up until they hit a critical layer and break. And so that's what we're trying to prevent that reflection. This is off by default. And I would say that in real data applications, I would always turn it on. The damping option we're using is option 3, and that's the one that's described here because we think it's the best general purpose approach to damping gravity waves. You can look in the tech note to see what it actually does. The default damping coefficient is 0.2, and the height below the model top where it starts being activated is 5,000 meters. That's the default when you turn it on. So these are the parameters you can use and play with if you want to utilize that. The formulation shows here that it's got a sine squared profile in the vertical. So at the point where it starts, which in this case, for example, 5,000 meters below the model lid, that coefficient for the damping R will be 0, and then it'll ramp up to 0.2 when you get to the model top. Of what to look for in terms of whether you need this damping or not. Here's a simulation, a three-dimensional simulation, but we're looking at a cross-section through the Rocky Mountains. And Boulder, where we are doing this tutorial most often, and where NCAR is located, will be at the base of the major mountain that you can see there to the east. And what we're looking at is a vertical velocity field and potential temperature field. The potential temperatures are contoured. There are velocity vectors, and the vertical velocity magnitude is color contoured, red meaning up, blue and down. And you can see the big wave over the mountain. So this is on a 5-kilometer mesh, and what we're looking at are two simulations, and the solutions at 12 hours and 30 hours. At the top with that Rayleigh damping layer on, with those coefficients noted when it's on in the last slide, and at the bottom it's when there isn't the Rayleigh damping on, the gravity wave absorbing layer. And you can see the reflected waves on the bottom panel, particularly at 30 hours. The wave reflection is very clear, and these are just spurious. So again, I think for real data applications, you should feel comfortable having that on in your default configurations, even though it's not on in the default ARW configuration. There are a number of projection options that you have in the ARW model, and these projections are part of the dynamics, but you've heard about them, or we'll hear about them in other lectures. In the idealized cases, you can use Cartesian boxes, both 2D and 3D. And then when you go to the sphere, you essentially have 4 different projections that are available to you: a Lambert conformal, polar stereographic, Mercator, and you can use a latitude-longitude grid. The top 4, 1 through 4, share the fact that they're isotropic, meaning that the grid always has the same ratio, delta x to delta y. And the map scale factors, which are essentially a measure of that ratio, or the map scale factors compared to each other are also a measure of that ratio that show up in the equations of motion. In the projections are always equal. However, the latitude-longitude projection isn't equal. For example, the north-south direction will typically stay the same, like delta y, but delta x, which is the east-west dimension of a grid cell, will shrink as you go towards the poles because it's on this latitude-longitude grid. So those are anisotropic projections. This is what you have available to you in ARW right now. If you wish to perform global simulations, you can configure WRF to run globally, and it runs on a latitude-longitude mesh in that configuration option. It also employs Fourier filtering, or otherwise known as a version of polar filtering, to stabilize the solutions, because those converging grid lines at the poles cause stability problems, because delta x gets smaller and smaller as you go towards the poles, till all of a sudden it goes to 0, obviously, at the pole. This is a classic formulation for a polar filter, and it's available for your use. However, if you really are interested in global simulation, you should consider our other model that we've constructed and support for that use. That model is called the MPAS model, the model for prediction across scales. In its quasi-uniform mesh that it employs, it is an icosahedral mesh, a classic icosahedral mesh. But it also allows for variable resolution. You can generate your own variable resolution meshes to embed refinement, and that mesh very smoothly, and it performs significantly better for simulations where you want to add refinement compared to the approaches used in WRF, specifically the nested grid approach. So MPAS is available. The numerics within it look very much like the WRF numerics that you've seen in this talk. It uses many of the same physics you've seen also described in this tutorial. So if you're seriously considering employing a global model, look at MPAS. You have a number of boundary condition options available in the regional WRF configuration. Real data, you're going to be using specified boundary conditions. Those are coming from wherever you get them, from specifying values from other analyses, from reforecast, straight from observational analyses, whatever. But those we use specified boundary conditions. We also have open lateral boundaries, which are radiative conditions, which are used in idealized cases. Also symmetric lateral boundaries or free slip walls that are also used in idealized simulations. Periodic, used in idealized simulations. And nested boundary conditions, which are effectively the specified boundary conditions, but those specified values are coming from the outer nest running in the nested conditions. The upper boundary condition, there's a constant pressure upper boundary. That's the default in WRF. You also have available a rigid lid. You can read about that in the tech note if you wish to know more about that. Sometimes it's used in LES configurations, but the constant pressure, the difference between the constant pressure and the rigid lid really doesn't make much difference in most of the simulations that we do. Bottom boundary condition, essentially the dynamical core sees the bottom boundary as a free slip, but once you turn on physics, then all the surface drag and surface fluxes that come along with that are there, so it's no longer the free slip condition that's applied. So what we've talked about today is essentially how the solver works, all the code that implements that solver for the Advanced Research WRF model is sitting in the dyne_em directory below the main WRF directory. If you want to know more about how the solver works and want to look at the literature concerning how it's been set up and everything, I really strongly recommend that you look at the WRF-ARW tech note. It's online, and we've been working very hard to try to keep it up to date. Right now, it's up to date to version 4.1. Going from 4.1 to 4.2, there weren't many major additions to the model that required updating in that tech note, but we'll be updating it again, I think, for the next release likely, or at least soon thereafter. So I hope this tutorial lecture was helpful to you, and thank you for your time and attention.